G'day everyone, it's Alex again, back on episode 2 of learning electronics through experimentation. Today I'm going to be talking about the resistor and how that can be wired up in series and parallel. There'll be a very basic amount of maths that we put into this, and I'm just going to do some examples following along with the book again, showing how they can be used as voltage dividers and the purpose of them. We'll just do a quick discussion on what a resistor is and sort of the applications of what resistors are generally used for. So I'll take you down on the table and I'll see you down there. Hi everyone, so we're back down on the table now. I've just drawn up the schematic for the project that's in the book, just so I can draw some notes on there, add some to the side, and sort of extrapolate more information that might be given to us compared to the small blurb of text that's associated with this one. So in this project, I believe it's just trying to let us know that when we connect resistors up in series, it's going to change the amount of current that flows through them, and that resistance is just added up when it's connected in series. So in this case, we can see that we have two 470 ohm resistors connected in series, and depending on the position of this switch, which you can see here, determines whether the current flowing through the battery, the LED, will then pass through either two resistors or just the one resistor. So a little thought experiment would be, what do we imagine will happen? In this case, it is mimicking the circuit of passing through two resistors. So what do we think will happen to the LED when we flick the switch? A smart guess would be that more current is going to flow through, and the LED will shine a little bit brighter. So if we just go ahead and do that, correction, I had that around the wrong way. So now it is currently facing upwards. And then if I were to put it forward, you'll see that it increases in luminosity just a little bit. Yeah. Right, so what's happening here can be described with Ohm's law. Some bloke back in 17 something or other, or 18 something or other, I think his name was Simon Ohm or George Ohm, I don't really know, sorry to whoever that is, discovered the relationship between voltage, current and resistance. And he put it into a mathematical formula, V equals IR. You might be familiar with it, it's probably the first thing you'll ever learn if you're dabbling in electronics. So we can determine how much current is flowing through the LED if we apply Ohm's law to this circuit. So in this case, we will first have to find out how much voltage drops across an LED. This isn't something I've touched on yet, but we can do that either by looking at a data sheet for a red LED, which I'll try and bring up on the screen right now if I'm technically savvy enough. Otherwise, a much easier way to do it is to just find one, like an identical one, or pull it out of the circuit, and then bring out a multimeter. And any decent multimeter worth its weight will have a function called the forward diode check or something or other. It just checks the voltage that drops across a diode when it is forward biased, meaning that the voltage is applied correctly to it. We'll touch on diodes a little bit later, I imagine, but in this case we can see we look at an LED, the longer LED leg is the positive one and the shorter one is the negative. So using my black probe on the negative, I'll just bring that out a bit so I don't short it, and then my red one on the positive, and changing this to actually diode mode, we can see that light up and it drops 1.8 volts across the LED. So that checks out. Generally, I think most red LEDs will drop between 1.8 to 2.2 volts. So from there, we can travel along and know that 1.8 volts drops across the LED. If you're as bad as maths as I am, you need a calculator for everything. It'll be 7.2, but always just double check. 9 minus 1.8, 7.2 volts. So we know that from here, there is 7.2 volts of force effectively left to drive current through the circuit. And then from here, we can determine how much current will flow using this. We will have to transpose it a bit to solve for I, and what I mean by that is just rearrange the formula. So we will divide both sides by R to leave I alone. So V divided by R equals I. And then we can plug in our 7.2 volts and our 940 ohms, which is the result of adding up our resistance of R1 and R2. And so we get 7.2 divided by 940. Plugging that one in the calculator, 7.2 divided by 940 is approximately 7.6 milliamps. So if you get a decimal like that, just times it by 1,000 and, you know, use your engineering notation if you'd like. So yeah, I don't know what I'm going with that. 7.65 milliamps. So traveling around this way, .65 milliamps. And then just as a proof of concept, I'm going to use my multimeter to connect up to the circuit and see whether that's actually what's happening. So changing our leads to measure for current, milliamps, and the earth, putting that on milliamps. And when you're reading a circuit like this, we just have to make this part of the circuit. So if you can see, that's fine. That will go there, and this will go there. And I'm actually getting 14 milliamps. That's because I have the switch set the wrong way. So sorry, 1 second. 7.45, that's a bit better. So it's not exact, and you just sort of have to get used to that. Oftentimes when you're using components, there are going to be tolerances that I have to touch on as well. There's heaps that you have to touch on, and you sort of just have to accept that you're not going to know everything as you go, and you'll just pick it up. As horrible as that sounds. All right, sorry. So just to elaborate a bit on that, I just want to emphasize that you can't get too stuck up on exact values when you're sort of doing a bit of circuit analysis. So in that case, we had the 7.4 milliamps when we determined that it should be probably closer to 7.2, even though I didn't finish. Sorry. We determined it should be 7.65 milliamps, and we got something slightly different. And so why is that the case? Right, so oftentimes, like pretty much all the time, when you're working with electronic components, it's just the nature of physical things, like nothing's going to be perfect. Like there's manufacturing differences when they're putting all these materials together and they're going through the refinery process, however you want to say it. Anyway, so I think that's a good time to sort of touch on what a resistor is, and how to identify one. All through-hole resistors, that's all I'm going to be working with. I'm not going to work with service mount components because we can't really see too much going on there. But in the meantime, resistors will generally have 5 or 4 bands on them, and each of the bands is correlated with a different value. Black being 1, black being 0, brown being 1, and red being 2. You'd sort of just have to memorize this chart. You can make a little rhyme for yourself to remember the order. I think it's just how they would appear in the rainbow, maybe? Who knows? Red, orange, yellow, green. Yeah, it's pretty similar. Anyway, so the first value represents the first, reading it from left to right, it's hard to sort of determine, but I think it's generally the thickest band is the first number to go off. So we have a brown band, which is a 1, according to this, and then we have 3 black bands. And so looking at this, we can see that black is representative of 0, and these are just, so it's unfortunately not saying it on the card. In a 5-banded resistor, the first 3 ones are the actual decimal representation of what the value of the resistor is, and then the 4th band will be a multiplier. So in this case, we have 1, 0, 0, denoted by brown, black, black, and then we have another black, so it would be times 10 to the power of 0, which equals 1. So this resistor should equal 100 ohms. And I'll show that to you in just a second. Finally, there is a 5th band, which is about the tolerance. So this is how much the described resistance can vary from what it actually is due to manufacturing errors. If you spend more money, you'll generally get ones with tighter tolerances, but at the end of the day, if you're just doing hobbyist electronics and you're not working on some crazy new high-tech gear, I'm sure you can get away with like a lot. So in this case, we have a brown one referring to the sheet. We can see that means it has a tolerance of plus or minus 1%. Plus or minus 1% of 100 ohms is just 1 ohm. So when we measure this, we can expect it to be either 99 to 101 ohms. So we'll just bring that one out just to, again, confirm it through experimentation or whatever I'm sort of crapping on about. So we just have to set our multimeter to measure for ohms, 200, chuck our lead back into the one indicating that it measures resistance. And if I bring this up here, go across it, ideally you shouldn't be using your hands because that will add different paths for it to travel through and will alter how much it is, but we can see that's actually really close to 100 ohms as we sort of calculated. You don't even have to learn all this stuff about reading color codes. Most of the time, when you like building circuits and stuff, they will be nice enough to print the value of the resistances on the casings. And if you're pulling them out, it's always just good to measure them with the multimeter anyway, because sometimes it is hard to tell the difference in colors between maybe like a red and an orange or something if you're a bit hard on seeing. So that's sort of just a 5-minute how-to on what a resistor is and how to read the values of them. So, 1 second. And I suppose while I'm sort of going through components as they're introduced, I'll briefly touch on the LEDs as well. So LED represented by this, how would you call that, a symbol on the schematic or the circuit diagram, represents the LED. They stand for light emitting diode, so we'll touch on it later, but this triangle with an arrow indicating the anode and cathode, meaning the positive and negative side of a diode, is why it's sort of drawn like that, and then arrows sort of indicate that light is emitting from this. There are normally, there's a fair few different types of LED colors now. They're not actually just different because of the housing that's on them, as I originally thought. A lot of work actually had to go into creating different colors of LEDs. They have different chemical compositions inside that react differently, obviously, when current flows through them. So before I was saying that red LEDs typically drop 1.8 to 2.2 volts across them. That's different for different colored LEDs because of those different chemical compositions that exist inside of them. So it's from memory. Blue LEDs are the most power hungry ones. They require the most current to drive them, and obviously they drop more voltage across them as a result of that. So in this one, I have a blue one. I would expect something higher than 2.2 volts being the maximum of like a red, because yeah, blue is a very hungry boy. So measuring the voltage drop across this, we get, as expected, 2.5 volts. So depending, later on when you're designing circuits yourself, just take note of the power requirements of different colored LEDs. Again, I'll bring it up on a schematic. What do you call them? Well, here it is. Here's the part specifications. Bang, here we go. Boom. You can look up the current that a LED is capable of handling, and when you exceed that, you can expect it to burn out. So whatever this one is, I'm just envisioning one in my head, and then I'll bring it up on here. 1 second. All right, yeah, so looking at a red LED, I can see that the maximum forward current is 20 milliamps. So that says if we drive more than 20 milliamps through it, it will extinguish the component, and it's going to be irreparably damaged. So we can sort of work that out, and this could be like your first sort of circuit that you may design yourself. You want to drive an LED with the maximum power output before it extinguishes. So this is a case where a bit of maths actually comes in handy. So in this case, keeping in mind that an LED is going to drop 2 volts across it, and we're going to use, we'll say it drops 2 volts instead of 1.8, and we're going to use 9 volts as our power source. What would be the minimum resistance to get the maximum current through the LED before we explode it? And then we'll actually test that and do a little proof of example there. So assuming we have 7 volts, because we're going to use a red LED again, we need to solve for 20 milliamps in this formula. 20 milliamps, because that is when we have maximum drive through our LED, equals, we're going to use 7 volts divided by the resistance. And then we need to solve for R. So in this case, we will invert both sides, and we'll just times them both by R. I'm pretty dumb with explaining things. So 20 R equals 7, and then R equals 7 divided by 20, which equals 7 divided by 20. What have I done wrong? Really? 0.35 ohms. 1 second. Oh, my bad, correction on my last. I forgot that when you're doing these, you have to keep everything in the same like times 10 notation. So I can't be using milliamps, I have to be using amps, because that's how the equation is written, where I is equal to amps, not milliamps. So I just have to write this as 0.02. So fixing that up, getting rid of the M. Again, that's why I'm doing this, just to sort of reinforce all these silly little things that I often forget. So 7 divided by 0.02, if you can see that, it's pretty terrible. Actually, you know what, I've got an eraser for exactly this reason, so otherwise I would have been doing this in pen to begin with. Divided by 0.02 equals 7 divided by 0.02, 350. So from our calculations, we can deduce that if we have 350 ohms of resistance, the LED will be shining with maximum brightness, assuming we have a 9-volt power supply and it drops approximately 2 volts across the LED. So I'm going to plug that in and we'll see it go, and then I'm going to drop it down to, we'll go maybe like 200 ohms after that, just to see if the LED does actually burn out as the specification says it potentially might. I think it'll hold for a while, but let's find out. Alright, so we've jigged up the circuit to represent this. I don't have any 350 ohm resistors. That's not a thing that actually exists in what would be like the standard resistor outputs, I guess. Like there are different ones that exist, but like generally they all follow these allocations of 0, 10, 20, 47, 47K. It's just like common resistors values that you'll come across depending on which like internationally recognized set you're using, I suppose. But so I've rigged one up that's approximately 350 ohms with the values that I had available. So on the multimeter, set to resistance, I have approximately 340 ohms. Close enough for what we're doing, right? Like I don't think it's going to matter. So we can look. The LED should shine with maximum brightness when I apply power to the circuit. And it appears to be working fine. We would watch this for a while. I imagine it might even feel the tiniest bit hot. It's still like no current passing through it, so I can't expect too much heat to be generated from that. But anyway, because the data sheet said approximately 20 milliamps, we'll check how much current is actually flowing through this circuit. So I'll pull this one out and we'll do what we did earlier with our multimeter, switching to measure current in milliamps, and I fully expect about 20 milliamps. So making sure I have the correct polarity and completing the circuit with the multimeter, we have approximately 20 milliamps. Look at that, pretty good, right? So let's try and destroy our LED by ignoring what the data sheet tells us to do. So we'll see how far we can go, right? This is a 20 ohm resistor, so we'll drop from 340 ohms to approximately 320 ohms. And just to verify that, oops, I'll get that on there. Sorry, I'm always messing up my probes, aren't I? Anyway, so yeah, 320 ohms, if you can see that. Let's see whether the multimeter can hold up to those currents, and we'll also see sort of what currents we're getting. So again, I just have to sort of dodge something up. I'll plug this one back in, and then I'll complete the rest of the circuit with the multimeter leads so that I can continue watching the current. So odds on it exploding, who knows? We'll find out. Again, I'm not in the correct probes and I keep going, oh geez, what have I done wrong? Here we go. Getting 21 milliamps. So it looks like the data sheet may have been lying to us. It did say continuous current at 20 milliamps, so it may eventually extinguish if we were to hold it like this for a while. So let's go a bit more extreme. We're gonna up it up to, I don't know, if we remove this resistor, and this is a 220 ohm one, I believe. Again, probes. We'll get there one day, guys. 220 ohms. So, what we did last time, V equals IR, we have 7 volts divided by 220. We're going to expect 31 milliamps to be passing through this circuit when we apply power to it. So I reckon that's enough to destroy our LED, but we'll find out soon, won't we? Again, I think we're... Aha, didn't catch me this time. Getting ahead of myself. Well, so that's pretty bright. Pretty close to the 31 milliamps we were expecting. However, the LED continues to fight through. Pretty impressive, right? And just because I need to destroy this thing, I'm going to plug in a much weaker one, and we'll see how low we can go. So I think this was it was either 100 ohm or 20 ohm resistor. Let's see what happens. And the LED died. You may have seen it briefly light up before it died. So now if I were to try and plug that back in with any other arrangement of resistors, we can see that the LED is actually cactus. It's blown up and current can't even pass through it. So effectively, we've created an open circuit and destroyed the LED. I will bring us over to the fast layout or whatever that simulation program is called. Again, I'll drop a link in the description below. So we're going to head over that way and we'll just briefly summarize everything that we went through today, describing how resistors work in series, how to read them, and what an LED is. And then as we go through further projects, I'll just sort of give an idea of like what, again, parts are doing and how they are generally used inside of a circuit. So I'll see you over there. 1 second. Alrighty, so I've gone ahead and drawn up the circuit that we were just playing with a few moments ago. As you can see, we have the two resistors set up in series and our 9-volt battery. I've set up a couple of probes just to prove that the simulations are checking out with what we were actually measuring before. So we measured a 1.8 voltage drop across the LED, and in this case we can see we have a 7.2 volt 7.2 volts of like EMF or electromagnetic force remaining on the other side of the LED. And again, when we move our switch, we will notice the current on the ammeter down here will change from 7, which is what we were reading when the switch was in the upright position, to approximately 14 or 15 in this case, because simulations always run a bit differently than real world scenarios. Not a great deal I really wanted to go over in this thing. I will only continue to do them if I feel they are necessary, just to sort of show how a simulation might be a helpful tool for those that don't have all of the components available to do any sort of like testing themselves. And it is often faster to mock something up in like a simulation than to do it on a breadboard. You know, to each their own really. Definitely when you're getting into, I believe, like sort of like radio electronics and stuff, it's definitely better using real world like parts than using a simulation, because there's a lot of interference that just sort of happens in the real world that I don't think current technology is like, well, software simulation is like good at mimicking. Any case, I will jump into the next video, I guess, which will be about resistors in parallel, and I'll do a little quick talk about that and we'll see how we go. So take care.